All right, in this work example, I'll be working through question 8 that was published in paper 41 from the ACE Physics syllabus code 9702. This one was administered in May, June of 2013. So it's about nuclear fusion. And the question reads, state what is meant by a nuclear fusion reaction. So we talked about different types of nuclear reactions. We talked about like radioactive decay, alpha decay, beta decay, gamma radiation, and then there's fission and fusion. So fission is when a large nucleus splits apart into fragments, right, that are about half the size. It's unlike an alpha decay where a large nucleus might just emit a tiny little alpha particle, a helium nucleus. So nuclear fusion is when smaller atoms combine, right? They fuse together to make heavier elements. They give us an example of one down here. So here you have deuterium and hydrogen that are fusing together to give us helium, right? So hydrogen fuses to helium. This is what's happening in the core of the sun. As it says right here, one nuclear reaction that takes place in the core of the sun is represented by this equation. And so we get energy out, the sunshine coming through the window right now is some of that energy. They give us some data here, and they want us to calculate the energy in joules released in this reaction. And then as a follow-up to that, they tell us that the temperature in the core of the sun is approximately, I guess, what's that, 16 million Kelvin? Suggests why such a high temperature is necessary for this reaction to take place. So we'll field that question once we've done the working here. So just a quick review of good old nuclear fusion. All right, so remember how we'll solve this. It should be that the mass of our deuterium, our 2.01410 atomic mass units, unified atomic mass units. That makes sense because there's a proton and a neutron. That's why it has a mass number of 2, but an atomic number 1. 1 means it's hydrogen. Anything with 1 proton is hydrogen. So this is just regular old hydrogen with a mass of 1.00728. But then this thing only has a mass of 3.01605. And so 2 plus 1 is 3, right? And we just round it. And so that all checks out, but is 2.01410 plus 1.00728 this? I don't think so. Otherwise, we wouldn't have a calculation to do. 8, 3, 11, carry the 1, that's a 2, that's a 0. So 3.02138 is a little bit more than 3.01605. By how much? 3 there, 3 there. Borrow or regroup, I should say. So does anybody remember what we call this? Go ahead, type it in the chat. What do we call this difference in mass between the reactants and the product? Does anybody recall what we call that? Like a deficit in mass. It's a defect. It's the mass defect. All right, so the mass defect is like the missing mass. And so that missing mass, that change in mass, must show up as energy. And so E equals mc squared. But we need to get this from unified atomic mass units into kilograms if we're going to get joules of energy. And so 0.00533 unified atomic mass units. And there are 1.67 by 10 to the negative 27 kilograms per unified atomic mass unit. So we multiply these two together. 0.00533 times 1.67 by 10 to the negative 27 gives us 8.9. 0.011 by 10 to the negative 30 kilograms. That's the mass. Times c squared remember that if C is 3 by 10 to the 8 meters per second, then you square everything. And so it's 3 squared is 9 by 10 to the way you square exponents is like adding them. So it's 9 by 10 to the 60. So sometimes because we're always using C squared in this, it's just helpful to remember that for C squared. Like you can remember C is 3 by 10 to the 8, that's an approximation, but 9 by 10 to the 16 is, you know, sort of the rough approximation of C squared. So it saves you a little bit of time. You have this number in your calculator, times 9 times 10 to the 16, and I get 8.01 by 10 to the negative 13 joules. All right, and they did want it in joules. So 8.01 by 10 to the negative 13. So you should get to that. Remember that the follow-up question was, the temperature is very hot in the core of the sun. Explain why that's necessary for this to go. So there's positively charged nuclei, right? This proton and this proton are both positively charged. And in order to crash them together and get them to stick to make a helium, you have to have a lot of collisions. And so temperature is really a measure of the average kinetic energy. It's like how fast are the particles sort of jostling around on the inside of the core of the sun. So the faster they're moving, the more likely they are to crash into each other and collide and stick together. And so you need really high densities and really high temperatures. You need lots of stuff in a small amount of space. And so the core, you know, stars are very dense, and you need high temperatures in order to make these reactions work. There are fusion, you know, reactors here on Earth with the goal of, you know, sort of harnessing, you know, this sort of energy. And they're very difficult reactions. And so the nuclear power plants that exist on Earth currently are all fission. They're all based on splitting apart the heavy things that the universe has already created, right? We mine the uranium out of the ground that the universe has already sort of made in those stellar explosions, like you see. Here. Exploding massive stars, right? You just make all this stuff and see the uranium down here, merging neutron stars. So when neutron stars merge together, they make, you know, all these heavy elements like that.